The Big Bang Theory begins with a singularity, an infinitely dense and hot point where all known physical laws break down. This singularity, smaller than an atom, contained the entire universe's mass. Around 13.8 billion years ago, its instability triggered a cataclysmic expansion. Quantum fluctuations in this state may have seeded future cosmic structures. Though unfathomable, this concept is supported by Einstein's general relativity and cosmological observations. In a fraction of a second, the singularity expanded exponentially, known as the Big Bang. Spacetime itself stretched, releasing immense energy. Temperatures reached over 10 to the 32 Kelvin, creating a plasma of fundamental particles. This inflation phase, theorized by Alan Guth, explains the universe's uniformity. Within microseconds, the cosmos grew from subatomic to astronomical scales, setting the stage for particle formation. As the universe cooled, the four fundamental forces separated. Gravity split first, followed by the strong nuclear force, electromagnetism, and the weak force. This phase, called the electroweak epoch, occurred at 10 to 12 seconds post-Big Bang. Particle interactions became governed by these forces, allowing matter to stabilize. Theoretical models like grand unified theories attempt to explain this separation. For the first microseconds, the universe was a searing soup of quarks, gluons, and leptons, particles too energetic to bind. Experiments at CERN's Large Hadron Collider replicate these conditions. As temperatures dropped below 2 trillion Kelvin, quarks combined into protons and neutrons. This quark-gluon plasma phase is critical to understanding how matter overcame antimatter in the early universe. 3 minutes post-Big Bang, temperatures cooled enough for protons and neutrons to fuse into atomic nuclei, primarily hydrogen, 75%, and helium, 25%, with trace lithium. This Big Bang nucleosynthesis lasted only 17 minutes, but determined the universe's elemental composition. The precise ratios observed today match theoretical predictions, validating the model. 380,000 years after the Big Bang, electrons bonded with nuclei to form neutral atoms, releasing photons in a flash of light, now redshifted into the cosmic microwave background, CMB. Discovered in 1964, the CMB's near uniformity supports inflation theory. Tiny fluctuations in its temperature map reveal the seeds of galaxies. This afterglow is the oldest light we can observe. For 200 million years, the universe was dark, filled with neutral hydrogen gas. Gravity slowly pulled matter into denser regions, igniting the first stars around 150 to 200 million years post-Big Bang. These population 3 stars, massive and short-lived, fused hydrogen into heavier elements. Their ultraviolet radiation reionized the universe, ending the dark ages and enabling light to travel freely. Over billions of years, stars clustered into galaxies through gravitational attraction. The Milky Way formed around 13.6 billion years ago. Hubble observations show early galaxies were smaller and irregular, merging over time to create spirals and ellipticals. Dark matter's gravitational pull played a key role, providing the scaffolding for visible matter to assemble. In 1998, observations of supernovae revealed the universe's expansion is accelerating, driven by dark energy, a mysterious force making up 68% of the cosmos. This discovery earned the Nobel Prize. While gravity pulls matter together, dark energy pushes space apart, leading to a future big freeze where galaxies drift beyond observable limits. Its nature remains one of cosmology's greatest puzzles. The Big Bang theory is supported by Hubble's law, CMB uniformity, and light element abundances. Yet mysteries persist. What triggered inflation? Why does dark matter not interact with light? Future telescopes like the James Webb aim to probe earlier epochs. Competing models like cyclic universes lack the Big Bang's empirical weight. The quest to understand our cosmic origin continues.